In 12.2, we're going to look at polar coordinates. And then we're going to translate back and forth between polar coordinates and Cartesian or rectangular coordinates. This comes up a lot in calculus. Oftentimes, it's easier for us to compute things like integrals when we're in polar equations rather than in rectangular xy equations. Because polar equations are more efficient when you're working with circular motion. If we look at this rectangular coordinate system, and let's say that we were going to graph the point, let's look at 1, 2, 3, 4, 4. That would be this point here. Remember, this is in Cartesian or rectangular form. And the movement is linear. When you think about it, you're going to go a positive 4 in the x direction, and that would be a horizontal movement, and then you're going to go a vertical movement in the y direction, 4 units. So when we describe this motion in terms of polar coordinates, we're going to be graphing an r value and a theta value. The theta value is the usual theta that you remember from trig. So typically our theta value starts at 0 and we move counterclockwise. But first what we're going to do is we're going to go ahead and drop a right triangle. And we're going to see if we can describe this theta value. So if I look at let me look at a different pen. If I look at my angle theta, I notice that the side opposite of theta is 4. The side adjacent to theta is 4. So opposite over adjacent would be our tangent of theta. That would be equal to 4 over 4, or 1. So tangent is equal to 1 in quadrant 1 when theta is equal to pi over 4. So I have my theta value for my polar coordinate. I just need my r value. But the r value would just be the length of the hypotenuse for this right triangle. And this r value is going to be square root of 32, which turns into 4 square root of 2. In polar coordinates, I can describe the same point as 4 square root of 2, comma pi over 4. So it's always r and then theta. Normally when we think of r, we think radius, and we think positive values. But recall in polar coordinates, our r values can be negative, they can be positive, they can be 0. And that would be the same for theta. Theta can be negative or positive. When theta is positive, we're going in the counterclockwise direction. When it's negative, we're going in the clockwise direction. So let's move on to graphing some points. Example 1, part A, we're going to graph the point r equal to 1 and theta equal to negative 2 pi over 3. When I graph in polar, I typically look at my theta value first. So first of all, when theta is equal to negative 2 pi over 3, I'm going in the clockwise direction. So this positive 4 pi over 3 is actually my negative 2 pi over 3. So I found my theta, and now I go a positive r 1 unit. And this would be the point. I'm going to label this as A. This is the point in part A. Part B, r is negative 4. Theta is 2 pi over 3. So I look at my 2 pi over 3. Since r is negative, instead of going 4 units towards my theta in quadrant 2, I'm going to go in the opposite direction of my theta 4 units. So 1, 2, 3, 4 should be here. And that would be my point B. Part C, r is 4, and theta is 5 pi over 3. So first of all, I find my theta 5 pi over 3, and then I go a positive 4 units towards that theta, since r is positive, 4 units. I actually end up at the same point as B. So remember, in polar coordinates, there's going to be infinitely many ways to describe the same point, since r's can be negative or positive, thetas can be negative and positive. Plus, remember, theta can keep going plus or minus 2 pi, and you're still going to be at the same point. Whereas in rectangular coordinates, xy coordinates, there's only one way to describe a point. One of the first things we want to do is we want to make sure that we can go back and forth between our polar coordinates and our rectangular coordinates. In this box, we see the relationship between x and y and r and theta. X is always r cosine theta, y is r sine theta. R squared is equal to x squared plus y squared, and tangent of theta is y over x. In example 2, we're given an equation in polar coordinates, and what we want to do is we want to change this to Cartesian or xy coordinates, and then, if possible, describe the curve. So my first thing to do is see if I could substitute any of these r's and thetas with x's and y's. And the way it's written, I can't. However, I do notice that I have a sine and I have a secant. Secant is not listed, only sine, cosine, and tangent. So maybe my first step could be to get rid of the secant squared and write it as 1 over cosine squared. So at least I have a cosine in there. This is not the only way to approach this problem, and oftentimes you'll find that there's many ways to go from polar to rectangular. But the glaring thing for me was that there was a secant, and I don't see secant listed anywhere in the box above. So maybe I can split up this cosine squared and write this as r equal to sine theta over cosine of theta, because I know that will give me a tangent, which I have listed, times 1 over cosine of theta. So r is equal to tangent of theta, which I can then replace with y over x. Well, I have gotten rid of some of the thetas. Now, if I had an r times cosine of theta, then I could replace that with the x. So at this point, I think I'm just going to multiply both sides of the equation by cosine. And that will give me an r cosine of theta on the left, y over x on the right. All right, so now I can replace the r cosine of theta with an x, which would give me x equal to y over x. And I'm done. This is an equation in Cartesian coordinates. However, I don't really recognize the equation the way it's written. Maybe if I multiply both sides by x to get x squared equal to y, and then rearrange, I'll get y is equal to x squared. That's something I recognize without a calculator. So that would be a parabola. But that's just the general shape. The general shape is parabola. Where is this? Well, I know the vertex is 0, 0. I also know that it opens up. What else do I know? Let's see, I don't have any, my xy intercept is the same as the vertex, so that doesn't help. So I know where the vertex is. I know it opens up from the vertex. I just need to know how wide it is, so maybe I can get a point that's passing through it. When x is 1, y is 1. So this also passes, through the point 1, 1. And I think that's sufficient. That's specific enough. There's only one parabola with a vertex at 0, 0 that opens up and passes through 1, 1. Okay. So again, if possible, try to get it as y equal to, or get it in a form that you recognize as like a parabola or a line or a circle or an ellipse or something like that. Again, there's a lot of choices when you're going from polar to rectangular. However, in example 3, we're going from rectangular to polar coordinates. And that's easier because you can always just replace your x with r cosine of theta. And then you can replace your y with r sine theta. And this is an equation in polar form. I don't have any more x's and y's. Everything's r and theta. I don't recognize this, and I can't really graph this in a graphing calculator, which you are allowed on the exam. So perhaps I can try to simplify this a little bit. Maybe get rid of the parentheses and see what happens. I'll have r squared cosine squared theta plus, foiling this out, we have r squared sine squared theta minus 2r sine theta plus 1 equal to 1. So right away I can see I can subtract 1 from both sides. And then looking at the first two terms, if I factor out the r squared, notice that I'm left over with a cosine squared theta plus a sine squared theta, which I know will just equal 1. So the cosine squared plus sine squared is going to be 1. And I have r squared minus 2r sine theta equal to 0. So I still haven't solved this for r, but maybe if I add the 2r sine theta to both sides, and then divide by r, I can get something that's simplified and also something that I can put in my graphing calculator if needed. In our next example, we're going to graph a polar equation, but we're going to do it by hand. Now, it's not really necessary for you to be able to graph by hand, but you should know how to do it, again, because you will have your graphing calculator. So this first equation I could just put in my graphing calculator and see the shape, but why don't we go ahead and do this by hand, see what happens. So I'm just going to make a table of values where I have r values and theta values. I'm going to put different theta values in. I always start with theta is equal to 0. And then if theta is 0, cosine of 0 is 1, so r is 3. This is going to, pass through 1, 2, 3, this point here. And then I'm just going to go around my circle, maybe try a pi over 6. Cosine of pi over 6 is square root 3 over 2, so r is 3 times the square root of 3 over 2. Now, I know from graphing before with my trig values that this is about, the square root 3 over 2 is about 0.9, so times that by 3, it's about 2.7. I could be a little off, but remember, I'm just sketching a graph, so it won't be off by much, maybe a 0.1. At pi over 6, I'm going to go out 1, 2, and about 0.7. This is a nice smooth graph, so it should do something like that. Next thing I'm going to do is go to pi over 4. That's actually not on my graph, so let me just write that in. Cosine of pi over 4 is square root 2 over 2 times 3, so this is going to be 3 times the square root of 2 over 2. Square root 2 over 2 is about 0.7, so times that by 3, this is about 2.1. At pi over 4, I'm going to go out 2 and a little bit more and continue on. Let's try pi over 3. So at pi over 3, cosine is half. So this becomes 3 over 2, or 1.5. Okay. And then at pi over 2, cosine is 0, so r is 0. And I'm back at the pole. Now if I keep going on, say I go to 2 pi over 3, that's going to give me a negative 1.5. So at 2 pi over 3, I'm going to go in the opposite direction, negative 1.5. And it looks like I'm coming back around, which makes sense, because let me look at these 2 points here. This is where r is positive 1.5. This is where it's a negative 1.5. And there's sort of that symmetry here. This has symmetry about the x-axis. Okay, so notice that this is r comma theta, and here this is negative r comma theta. So the theta stayed the same, but the r flipped, which means symmetry about the x-axis, and we'll talk about that in just a little bit. All right, if I keep going around, I'll end up back here when that's pi, I believe. So cosine of pi is negative 1, so r becomes negative 3. So if we go out to pi and we go negative 3, we're back where we started from. Which means for one cycle, my theta values would need to go from 0 to pi. After that, what's going to happen is this will just keep cycling around. So as your theta values get larger and larger and larger, we keep circling around the same path over and over again. We're going to look at a special case. So this is a case where the equation has theta. It doesn't have an r in it. So think back to your xy equations. If you have an equation with just x or just y, that's a line, either vertical or horizontal. And that's the same for polar. If you have an equation with only a theta, what you end up with is a line. Because it really doesn't matter what r is. I'm going to make a table of values. R theta. Now remember, if theta is pi over 3, r can be anything. R could be 0, 1, 2, negative 1, negative 2. It doesn't really matter because theta is always pi over 3. So if I were to graph these points at pi over 3, r is 0, r is 1, r is 2, r is negative 1, negative 2. And then notice I could keep doing this. What I end up with is this line that passes through the origin. So it turns out that if theta is equal to any value a, then this is going to be a line through the origin. But instead of origin, I'm going to just say pole. Okay, so that you cannot put in your calculator because your calculator will only graph polar equations that are r equal to. So some people prefer to graph in a rectangular coordinate system or a Cartesian coordinate system first because that's more familiar to them, which you can do. So another way to graph by hand is to graph the function on a Cartesian coordinate. If I look at my axis and I use a Cartesian coordinate, I'm not going to use x and y. My x-axis I'm going to call theta. My y-axis I'm going to call r. So I'm going to put in a theta value and I get back an r value. So once I have this graph, then I can use this Cartesian graph to sketch the graph of the polar curve. 1 plus cosine theta. So cosine of theta, we know the graph for that. Adding 1 just shifts it up 1. So at 0, I'm going to pass through the point 0, 2, and then at pi over 2, it's going to be at 1. At pi, it's at 0. 3 pi over 2, it comes back up again. At 2 pi, we're back at 2. So since I got back to 2, I'm going to stop there, because that will probably give me 1 cycle. So now I'm going to translate these points to the polar graph. I'm going to start out with the point r is 2, theta 0, and then at pi over 2, r is 1. So I'm thinking it curves around to connect those two, but I didn't figure out pi over 6, pi over 4, pi over 3, but I really don't have to. If you go back to the Cartesian graph or rectangular graph, you see that r starts at 2. And then as we move to pi over 2, the r values are getting closer and closer to 1. So as I move to pi over 2, the r values are getting closer and closer to 1. Kind of a sad graph. At pi, I'm back at the pole. So notice that for all these intermediate values, my r value is still positive, but it's getting smaller and smaller and smaller and approaching 0. So that's looking at this piece of the graph from pi over 2 to pi. Now from pi to 3 pi over 2, so I'm in quadrant 3, my r values are going from 0 back up to 1. At 3 pi over 2, I'm at 1. So I got positive r values starting out really small and then getting larger and larger, which means it will do something like this. And then from 3 pi over 2 to 2 pi, the r values are going from 1 to 2. So they're getting larger and larger and larger. And this completes my graph, my sad graph. That's too much work for me. Oops, sorry, I made a mistake and hit pause. I usually don't like to go from Cartesian to the polar graph. I usually just graph the polar graph. But I did talk about this in our previous example, is this idea of symmetry. So there's symmetry about the x-axis if r theta and r negative theta are on the same graph. So if we look at this first diagram, we have an r theta and an r negative theta. So this particular graph shows symmetry about our x-axis. If we want to look at symmetry about the y-axis, or reflecting about the y-axis, then if you have an r theta, you need to have a negative r and negative theta. And that would be symmetry about the y-axis, but for some people it's easier to see this as a positive r and then a pi minus theta. So symmetry about the origin means that you're going to rotate 180 degrees. So if you have the point r theta and you have the point negative r theta, which would be the same theta value, you just go in the opposite direction, then what you've done is you've rotated your graph 180 degrees. Okay? You can also look at this as r theta and r theta plus pi. I personally don't use symmetry when I graph, but some people like to use it. I just plot points. On this next page, these are just some common graphs that you might see. We talked about just having a theta equal to a number, and that would be a line through the origin. But there's also an r equal to a number. So if r is equal to a number and there's no theta in the equation, it's just going to be a circle centered at the origin. We looked at the case where r was equal to a cosine theta. Ours was 3 cosine theta. And we ended up with this circle. Okay? If it's r equal to some number times sine of theta, you get a circle as well. It's just going to be on the y-axis because sine is a y. Cosine means you're on the x-axis because cosine is an x value. We also have this spiral, which would be the last graph. It spirals outward. That would happen if r is equal to some number times theta. Now, depending on whether a is negative or positive, would change the direction of the spiral. So in that case, the graph will never come back onto itself. We also have these limacons. They look like hearts. In the case where a is smaller than b, you end up with this loop. In the case where a is equal to b, and we already graphed something like that, we end up with this heart shape. So it comes around, just touches, and it comes back around. So for these particular examples, these are all with the sine function. We graphed this cardioid, this heart, with the cosine function, which meant that it shifted onto the x-axis because cosine goes with the x value. If a is greater than b, which would be this third graph, then it still looks like a heart. It's just getting rounder. And then if a is greater than or equal to 2 times b, you end up with this circle, sort of. It's a little bit flat, but it's like a shifted circle. We also have what's called roses. The roses depend on whether in the argument this n value is even or odd, and that gives you how many leaves of your roses you have. Again, you can put these in your calculator. Just do a few examples to verify. We have a lemniscate, which is just a figure 8. If it's a sine, it's doing this diagonal figure 8. And if it's a cosine, it's along the x-axis. You can always use these if you recall them instead of using a graphing calculator. Sometimes when we sketch, we're sketching regions, not just curves or lines. In example 7, we're going to sketch the set of points. Looking at this set, I can see that my r values are going to go between 2 and 5. The absolute value of my thetas are less than or equal to pi over 6. I'm going to go ahead and get rid of the absolute value on theta. It's easier for me to see, so remember to get rid of the absolute value. We're going to bound theta between the negative pi over 6, or put theta between the negative pi over 6 and the positive pi over 6. The first thing I want to do is I want to identify those theta values on my graph. So I have my positive pi over 6, negative pi over 6 corresponds to positive 11 pi over 6. So my theta values are going to go between this negative pi over 6 to the positive pi over 6. Now I'm going to look at my r values. So when theta is negative pi over 6, the r values go from a positive 2, so they're going to go in the direction of that theta value, to a positive 5. Is that right? 1, 2, 3, 4, 5. Yes. Now as my thetas go from negative pi over 6 to pi over 6, my r values are going to still remain from 2 to 5. So this shaded region is the set of points. This satisfy this set. Something else that may come up is finding the intersection of two polar equations. And this will come up a lot when you're trying to find limits of integration, when you're taking an integral of polar curves that intersect. And we can do this algebraically. Normally when we find points where graphs intersect, we set them equal to each other. So notice that I can set the 2 sine theta equal to the 1 plus sine theta. And then I can solve this equation for theta. There is a problem though, and that would be at the pole. When r is equal to 0, it doesn't really matter what theta is. Okay? So with polar graphs, algebraically you can find thetas where they'll intersect, but they also might intersect at the pole. Okay? So you always graph your equations to see if the graphs intersect at the pole. So you want to check the pole to see if they intersect at the pole. So for example, if I were going to solve this algebraically, I would minus sine of theta from both sides and get sine theta equal to 1. Easy enough. Sine is equal to 1 when theta is equal to pi over 2. But if this were a trig class, remember that if we add or subtract 2 pi, we're still at the same point, so I would plus a 2k pi, technically. And notice in these equations, if I put in pi over 2 for theta, now remember this is in polar form, then the first equation, the r value is 2, and in the second equation, the r value is 2. So 2 comma pi over 2 is a point where these graphs intersect, but is it the only point? So if I were to sketch a graph, and I'm just going to put those two equations in my graphing calculator, and I'm going to see picture-wise, do they intersect at that pole? Well, let's see. R equal to 2 sine theta, that's going to be a circle, and this is just a hand sketch. And then in my calculator, when I put 1 plus sine theta, what I get is a cardioid. Oh my god, this is horrible. Ew, that's terrible. It actually does this in my graph. Terrible, terrible, sorry. I'm so fired when it comes to drawing pictures. So I'm just going to darken the 2 points on my calculator where these intersect. So it looks like I have, because remember this is polar coordinates, this is pi over 2. It looks like the 2 comma pi over 2 I see, but also notice that these two graphs also pass through the pole. So they intersect at 2 comma pi over 2 and at the pole. Now I didn't really write down the points that they intersect at the pole because there's going to be different theta values. But that might come up on your MyLab. So the points would be, if you look at r equal to 2 sine theta, and you put in 0 for r, then you just have to figure out where sine of theta is equal to 0. And that first happens when theta is equal to 0. So with the first equation, it's going to pass through the pole at the point 0, 0. Remember, this is in polar. But when you look at the second equation and you put in 0 for r, then we're looking at where sine of theta is equal to -1. Sine of theta is equal to -1 at theta equal to 3 pi over 2. So when theta is equal to 3 pi over 2, sine of theta is -1 and r is 0. So for this second equation, it's going to pass through the pole at 0, 3 pi over 2. Which is why if you just set the equations equally to each other and solve for theta, you will get some of the solutions, but you might not get all the solutions. It depends if they both pass through the pole for different thetas. Okay, so that's it for our section 12.2. We'll go on to derivatives and integrals of polar equations in 12.3.